Okay, so in this video we are going to use the moment generating function of the general normal distribution in order to work out the moments of the general normal distribution. But we're also going to use it as an opportunity to recap the concept of random variables and functions of random variables. So this is the setup. Let's say we have some abstract probability space over here, which we'll call omega f and p. And then we've got some random variable here, x, which is going to map you onto the entire real line, such that x is normally distributed with mean mu and variance sigma squared, okay? So there we have some random variable. Now what I want to do is I want to set up another mapping, which I'm going to call t, which is going to map you onto a standard normal distribution. So I'm going to make a if I take the composition of these two, I want it to be a standard normal distribution. Okay, so we know that that if we have a general normal distribution, that x can be written as sigma times z plus mu. So basically that means that z is going to be x minus mu divided by sigma. So that's the transformation we're going to have to take. T is going to have to map any little x, so any x is an element of the real numbers. In this probability space here, it's going to have to map it onto x minus mu divided by sigma, and that therefore is the transformation which we could label as big X minus mu over sigma. And then what we want to do is that's going to map this onto the real line. So if you imagine having the real numbers here, then this function is going to map it onto, again, it's going to map it onto the real numbers. And it's going to take any little x here, it's going to subtract off whatever the mean is. So let's say the mean is, let's say this is 0, and this is the mean here. So it's going to subtract off that. So if we have 0 here again, it's going to, the x minus mu is going to be somewhere down here, and that's going to divide it by sigma. So let's say that is x minus mu. So it's going to get even smaller, or maybe bigger, depending on what the variance is, and it's going to go down to x minus mu over sigma. So it's going to map each point onto that. Okay, and the way that we're going to do this is that we want the probability space structure on here to be inherited from the probability space structure on here. So we want the probability. We want the CDF on here to be well. We want, okay. Let's just we need to give these probability spaces some names. So if we make this probability space omega prime f prime, the set of events, and the probability measure p prime, and we make this probability space, we'll label this omega double prime, f double prime, and p double prime. Then I want p double prime of some set. Let's say z is less than or equal to some little z. So we're taking the event. If you imagine this being the real numbers, and you've got some z here, I'm taking the event which is all real numbers less than or equal to z. So I want that as a corresponding event back here. So if you view this event, z is less than or equal to z, that has a corresponding event back here, because this is linked to here by the transformation t. So this is this is the event that x minus mu over sigma is less than or equal to z, because that's how you are mapping points onto here. If you imagine this being z, then we want all points that are to the left of z, and if we want to work out what set does this correspond to back here, it's all points such that all points little x are as an element of the real numbers, such that little x minus mu divided by sigma is less than or equal to z. So that's all points x such that sigma z plus mu, well, it's all points x such that they are less than or equal to sigma z plus mu, just by the ordered field properties of the real numbers. We're assuming that the standard deviation, well, the standard deviation is a positive number, so we can multiply both sides, and it's not equal to 0. So we'll have a multiplicative inverse, which we can multiply both sides by, and the inequality will remain the same, it won't flip. So that's perfectly fine. and we want, so that's the corresponding event. So if we say this number here, sigma z plus mu, is some number up here, and the corresponding event in this space is this one here, all points that are less than or equal to that. So we want, if this probability space is going to have the same probability space structure as this one, we want the probability of this event in here to be the same as the probability of this event in here. So we want it to equal p prime, the probability measure on here, of the p prime that x is less than or equal to sigma z plus mu. But this is just this is the CDF. We know what the p prime x is less than or equal to sigma z plus mu is, because we know that x is normally distributed mu sigma. So that is just the CDF of the general normal distribution. So that is